Hello, my name is Saul Javier Dominguez Leon, and I'm going to tell you about the nanomedicine. Nanomedicine consists of the application of nanotechnology in the field of health, with the aim of improving the quality of life of patients through the development of strategies aimed to the prevention, diagnosis, or treatment of illness and injuries through the use of devices, systems, and technologies that include nanostructures capable of interacting with molecular scale with the human body and its fluids. Thus, nanomedicine is emerging as one of the bridge of nanotechnology with the great projection in a near future due to its potential diagnostic applications and therapeutic. Nanomedicine is a relatively recent concept. Although the mentioned nanoparticles in relation to biomedicine appeared at the end of the 1970s, the term nanomedicine began to be used in years later, being today an area of research in growing developing. Nanomedicine tries to solve some of the problems related to disease such as cancer, cardiovascular ailments, diabetes, or neurodegenerative disease for which there are no appropriate treatments. Through the development of new methods of more accurate diagnosis, personalized therapeutic strategies, and more specific and effective disease monitoring than existing ones currently. All this through the use of tools and nanotechnology. In a generalized way, it can be established that nanomedicine encompasses three large areas: nanodiagnosis, nanotherapy, which includes the liberation controlled drugs, and particular applications in nanomedicine regenerative. The nanodiagnosis is based on the use of nanodevices as nanobiochips, nanoelectrodes, or nanobiosensors, and contrast systems for an accurate and rapid detection of a disease in its most stage early. Six, the development of strategies or tools based on nanotechnology to diagnose pathologies at the molecular or cellular level, both in vivo and in vitro. Ultimately, it pursues the early identification of alterations in the state of health of an individual in a reliable and robust way. In vivo nanodiagnosis requires that the system used be introduced into the organism, where it identifies and, on occasions, quantifies biomarkers that allow an accurate diagnosis to be established. This field involves a series of limitations, mainly related to the biocompatibility of the nanomaterials used. Therefore, for their application in clinical practice, it is essential to demonstrate its efficacy and safety. Classic examples of in vivo nanodiagnosis is the use of contrast nanoparticles in techniques medical imaging. Another example is system-based on quantum dots, nanoparticular semiconductors that are luminescent at the nanometer scale. These nanoparticles are made with semiconductors such as selenide cadmium and cadmium tellurium, and have size typically in the range of 2 or 10 nanometers. Depending of the size of the nanoparticles, they emit in different lengths of wave, giving rise to different colors. These nanoparticles can be combined with biological ligands that selectively target cells or tissues, making them excellent biomarkers for imaging techniques optical being used, for example, in the localization of tumors. In vitro nanodiagnosis doesn't present the complication of the necessary use of biocompatible or degradable nanomaterials, Since it is performance on samples of tissues and body fluids, allowing greater freedom when it comes to select the most suitable nanomaterial to obtain the highest specificity and possible sensitivity. An example in the area of in vitro nanodiagnosis is the development of nanobiosensors. Nanobiosensors are analysis devices capable of detecting chemical or biological substance without the need for fluorescence or radioactive markers. These devices are made of or a biological receptor for detection, such as antibody or enzymes, and by a traducer or sensor capable of detecting the recognition reaction of the receptor and transform it into a quantifiable signal. The nanotherapy uses, for example, nanostructures that contribute to the controlled drugs delivery preferentially into cell cycle. In fact, nanotherapies are not only a promising future, but that there are already a significant number of nanopharmaceuticals in the world today, marketed for the treatment of various diseases based on liposomes, lipid formulations, pegylated proteins and polypeptides, nanoparticles, polymeric, protein drug conjugates, and nanoformulations based on surfactants and nanocrystals. In addition, nanomedicines can enhance or complement drugs traditional, allowing them to specifically target cells and tissue seek, helping to cross biological barriers or releasing the principle active in a controlled manner in the presence of certain stimuli. The nanoparticles must also be biocompatible, degradable, and have a minimal toxicity. Another fundamental aspect is that they can be designed nanoparticles capable of not releasing the drug until it reaches the site where it has to be released. In this sense, controlled release systems of drugs have been refined over the years with the use of nanomaterials capable of responding a wide variety of stimuli endogenous, such as pH, redox potential, and availability of enzymes or reactive oxygen species, or exogenous stimuli, such as magnetic fields, temperature, light, which produce a change in the nanoparticle to release its content. In this way, a greater effectiveness controlling toxicity levels and reducing the effects secondary medications. However, nanomedicine approach not only allow to release drugs in a controlled way or detect disease early, but that also allow the development of strategies aimed to the prevention of disease. Nanotechnology offers new opportunities for development of vaccines, as in the case of vaccines against SARS-CoV-2, the case of COVID-19. Some of these COVID-19 vaccines use RNA molecules that allow protein expression and that go encapsulated in lipid nanoparticles that protect the RNA molecule until it is enters cells. In these cells, the expression of proteins occurs speckles of the virus, which are recognized by cells of the immune system that generate antibodies against the virus. The medicine regenerative aims to help repair or replace tissues and damaged organs using nanotechnology-based tools. Everything this contributes to nanomedicine, offering the possibility of treating disease which were not possible to address just a few decades ago with new approach. The main contribution of nanotechnology to medicine regenerative is the design of nanomaterials that improve biocompatibility or properties biomechanics of the materials used in this field. These new materials, which can be natural or synthetics, and can serve as support for cell growth with the creation of, for example, nanostructures that they mimic the extracellular matrix. In addition, these nanomaterials can be combined with the use of molecules bioactive that act as signaling agents of cellular action, modifying the behavior of cells and therefore offering the possibility of influencing in their proliferation, differentiation, etc. For the manufacture of this type of structure, is it possible to use 3D bioprinting technology, which offers a wide variety of possibilities thanks to the ability to adjust the layout manufacturing very precisely. Another possibility is the design of smart biomaterials that incorporate into their signaling molecules that, once on the parent's body, are released, gradually activating tissue regeneration in situ through the modulation of the mechanical and structural properties of the microenvironment itself. Already provides and will continue to provide benefits in the coming years in health thanks to the development of applications that allow the detection and early treatment of disease, their personalized early treatment, and further monitoring of its evolution more precise. Nanomedicine applications are mainly focused on fields on diagnosis and therapy, although it is possible to combine both to give rise to diagnostic strategies or provide nanotechnology tools in the new therapeutic strategies, such as advanced therapies or medicine regenerative. It should be noted that so far the applications of nanomedicine have been the development mainly in the field of oncology. However, in recent years, new areas for application are being explored, and it is anticipated that the development of vaccines for COVID-19 based on nanotechnology represents a turning point both for the development of new applications in nanomedicine and for approval by the regulatory agencies. Nanomedicine uses various materials that are chosen according to the application that seeks to develop the microenvironment of action, the way of administration, or frequency of use. The materials used in nanomedicine can be inorganic, like metals, salts, toxics, or bioorganic, like peptides, proteins, nucleic acids, lipids, polymers, synthetics, etc. These materials can also be combined in the form of hybrid materials that generally interact biomolecules with materials organic or inorganic and that respond as a single unit. An important aspect of nanomaterials is that they must be biocompatible and must be generally biodegradable, especially if they are to be used inside the human body, such as when they are used nanoparticles for controlled drug release. These materials, biodegradable, are suitable for chronic applications, and since they allow to have a wider therapeutic window, avoiding its accumulation in the body and the consequent toxic effects derived from it. Indeed, it is also possible the use of endogenous materials that the body recognizes as its own, metabolism, and are finally eliminated. In the case of manufactured nanopharmaceuticals with non-biodegradable materials, this must be excreted by the human body, since if they are not eliminated they can be used. This type of non-degradable materials are generally used in nanosensor and techniques imaging, or in acute single-use applications. Thanks to the great advance of nanomedicine in recent years, and especially to recent popularity of nanoparticles in vaccines against COVID-19, it is foreseeable that future developments and their translation in the field of health. In the future, one of the applications with the greatest impact will be diagnostic early that will allow the detection of a disease before the patient has symptoms. Thus, both the diagnostic imaging oriented towards the development of groups, contrast agents, or display systems, as the in vitro diagnosis aims at the detection of biomarkers and the development of systems or sensors that are increasingly sensitive and precise, will allow in the future detect alterations that occur on a subcellular scale in the body, offering the ability to detect disease in a very early stage. On the other hand, it should be noted that nanomedicine tends to use systems unique for the simultaneous combination of diagnosis and therapy, as far as known by the term theranostic. In the future of nanomedicine, thanks to technological advance, it is possible for us the possibility of developing implantable monitoring systems or biological parameters to warn about the presence of disease, or the avatar design of the human body created from a few cells and genetic information of each individual, which contribute to predict and prevent the appearance of disease, and serve in the study of various drugs to find the best treatments. You can also glimpse the design of autonomous nanorobots manufactured by a combination of nanoelectronics and biomolecules capable of selectively releasing drugs and carrying or nanosurgery in damaged tissues, or artificial organs developed from the cells of each individual. While these developments have not been materialized, some current studies already point to these technologies.